Okay, we have more than 20 participants. I think we may start. And first of all, I would like to announce the next, our seminar. Next week at the same time, we will have a talk from Peng Xu from Chinese Innovation Academy for Precision Measurement Science and Technology. He will talk about experimental progress towards quantum computation using neutral atoms. Okay, and now our speaker is Juan Torres from Institute of Photonic Sciences and Universitat Politecnica de Catalunya. And he will talk us about optical coherence tomography with an SU11 interferometer in the high parametric gain regime. Please.
Okay, thank you very much, Konstantin. And thank you to your department and university for this kind of invitation. So as you see in this, well, I will try to do it the best. I have to acknowledge that I am not an expert in doing this kind of online presentation. So please forgive me for thinking that maybe I'm not very clear. But as always, I mean, I'm open to questions at any moment. And so you have any question or you want to interrupt me, so please go ahead. So this is the title, as Konstantin said, I will like to highlight three things. So optical coherence tomography, that is a well-known technique that I will review very briefly for those of you who don't know what is that. Something somehow technical is SU11 interferometer that I will explain later, and then high parametric gain regime. This work has been done by these four persons that you see here. So Gerard and Gaetano. Gerard is my PhD student, and Gaetano is Masha PhD student. So is the person who were in the lab doing real things, not as in this case, in this particular case, myself and Maria. Although Gerard said that Maria always goes to the lab there to see what they are doing and what they are not doing. And then this work was done in Maria's lab in Erlangen, in Max Planck, where Gerard was visiting. So all this began, this is essentially a message for Sergei. Is there in Nottingham last year, where they invited me to give a talk, and Maria was there also, the laser physics, where I went to give a talk about optical coherence tomography and the work that we were doing. And then I said something that Masha pointed out is not correct, that it's difficult to get the high parametric gain regime. And very fast, Masha came to me and said, you are not right, it's very easy, so you can do it. So I was very happy to hear that, because in fact, we were looking for the experiments in OCT to have the high parametric gain regime. So Nottingham and the laser physics meeting was the beginning of all this collaboration between Masha and myself, Gerard and Gaetan. Okay, so we have the result of this cooperation is this paper that you have here, the experimental setup that I will mention, I will describe later. And now it's in the archive, it has been submitted and is under revision at this moment. It was submitted just one month ago. So you can go there and have more details about everything. So this is an outline of my talk. So first I will review very briefly what is optical coherence tomography for those of you who don't know too much about what is OCT. So I will refer as OCT as optical coherence tomography. Then I will briefly talk about different configurations, is what is called induced coherence configuration, SU11 configurations. Then I will explain how to use these configurations to do novel OCT scans or novel optical coherence tomography scans. I will talk about high and low parametric gain regime, because this is something important for our work. And then I will explain briefly the main result that you can see in the paper that I mentioned before. So what is optical coherence tomography? So it's something very simple. All of this began in '91. The first paper, this paper that you see here, optical coherence tomography, in the group of James Fujimoto in MIT, is the paper that most people mention when they talk about optical coherence tomography. This is a figure taken from this paper. But there's another paper that at the same time, you see 91, was putting forward the same idea, coming from Erlangen, precisely, is this paper. You see that the scheme is very similar to that. Probably, I mean, there are two main advantages in this paper. One is you see the journal, Science and Applied Optics. So this, to begin with, makes a difference. And the second thing is that these people, there are some doctors among the authors, applied directly optical coherence tomography to the retina imaging. And retina imaging is one of the main applications of optical coherence tomography nowadays. The people from Germany, they call it coherent radar, and they were looking, thinking more about surfaces and different, how to image surfaces. But essentially, the idea is the same in both papers, and both appears in 1991. So essentially, an OCT is a Michelson interferometer. All of you know what is a Michelson interferometer. You have here some sample. The sample has several layers. Here you have an example. And then you have here a mirror, a reference mirror that you can move. And here, what you detect. So what you detect is, let me move this. What you detect here, when you move the mirror, is something like that, what you see on the right. And this is the position of the moving mirror, that the reference mirror. So then you can see that you can image the different layers of the sample. And you can do it with very high accuracy. So normally, most systems nowadays commercially available, they can have less than 10 microns axial resolution. If you scan in the transverse dimension, so you can obtain a full image of something like the retina, for instance. No? So this is the idea. Nowadays, what people use, this is what is sometimes called time domain OCT, because you move the reference.
Juan, we don't hear you.
Something similar, so the scheme is the same. You don't hear me? Hello?
Yes, now yes.
Okay, it seems it has appeared a sign in my computer saying that the connection is unstable. So let's see. Yeah. Let me know if there's any other problem. Okay, so this is the same setup, but now what you look is at the signaling frequency. So you don't have to move anything. So there's no axial scanning. That is good, because if you want to do it fast, the less things that you move, the better. And now you have an spectrometer, and then you have a signal that is something like that. You make some kind of Fourier transform, and then you obtain certain peak that give you the same information than before. So this is what is called Fourier or spectral domain OCT, and we will do this in our experiment. We will use a spectral domain OCT. Okay. At the same year, curiously, the idea of induced coherence was put forward by the Rochester team led by Leonard Mandel. These are the two reference papers, this 91 and 92. One will be the equivalent at time domain, and the other will be the equivalent to a spectral domain. They are not doing OCT, they are doing induced coherence, but we will see that you can meet this idea with the idea of OCT. So essentially what they did is, let me use this toy plot from one of our papers, because it will be easier to understand. So you have a pan beam, you generate signal and Euler photons. The Euler photons can traverse an object that is lossy and can have several layers, and you want to know something about the object. And this Euler beam is injected in a second crystal where you have another signal photons and Euler photons. And you align perfectly Euler photons 1 and Euler photon 2. So in this scheme, what you measure is coherence between S1 and S2. And this is essentially an induced coherence scheme, as is the scheme that the Mandel's group demonstrated in 91. You can think, why not to see not only Euler 1 in the second crystal, but also the signal. So you want to see both output photons, signal, and Euler after the Euler has interacted with the object. So then what you have is a SU11 interferometer. So here you have a laser, you pan the crystal in the first pass, and you generate signal 1 and Euler 1. Euler 1 goes to a sample. You have several layers. Euler 1 comes back, signal 1 comes back, and the pan also comes back. And then you see in the second pass the nonlinear crystal with Euler 1 and signal 1. And this is what is called a SU11 interferometer. You obtain signal 2, and this is what you measure. And so you know the properties of signal 2. The difference with the induced coherence scheme is that now what is seeding the nonlinear crystal for the second time is both signal and islet, not only islet as it was in the scheme demonstrated by Leonard Mander's group. Okay. Recently, there have been, this is what is sometimes called nonlinear interferometer, and you can have a review here by Maria O in Advances in Autism Phonics. So people refer, or some people refer to this in general, induced coherence schemes or SU11 interferometer as nonlinear interferometers. So there has been recent activity, a lot of activity about this. You see this paper in 2014 by Anton Seilinger group, quantum imaging with undetected photon. Sometimes it's called undetected photon because they use an induced coherence scheme. So you see that the photons that interact with the object, the islet photons, are never detected. So this is what they say, that they measure things about the sample with photons, signal that have never interacted. It's true that there are correlation between signal and islet. This is another issue, but this is the origin of this term without undetected photon. And then you have this by this other paper where they did a spectroscopy with visible light. So you illuminate the object with one wavelength, maybe far infrared, and then you detect light with another wavelength that can be visible light. And this is this paper by Kalashnikov and co-worker. There are several papers. You see this paper here, where it is by the group of Franco Wurm and Jeffrey Shapiro, where they use very similar the title. You see classical imaging with undetected photons and classical imaging with undetected light. No? So they use the same. And the difference here is that they use different sources. They are not using entangled photons, and they are seeding. For instance, in this paper, they use a seed in the first nonlinear crystals in order to seed the first parametric down conversion process. There are other papers related to optical coherence tomography. This paper that is we did in Barcelona. This paper and this paper appear nearly at the same time. We are using an induced coherence scheme, and in the paper by Paterova and co-workers, they're using an SU11 interferometer. And you have a recent paper that has it's not so recent the paper, but it has recently appeared in the archive by the group of Sven Ramelow, where they use frequency domain optical coherence in a SU11 interferometer. All of these papers have something in common, that they work in the low gain parametric gain regime. They are doing OCT with a nonlinear interferometer, this paper with induced coherence scheme, and this other paper with SU11 interferometer. The first paper is doing time domain, and this second paper also, and the third paper is using spectral domain OCT. But all of them are working in the low gain parametric gain regime, in the low parametric gain regime. Sorry. In general, without entering into much details about the specific issues of sensitivity and so on, people mention two main advantages in this scheme. One is that you can have interaction with the sample at one wavelength, for instance, infrared, and then you can have better penetration depth into the sample, but you detect at another wavelength, and you can choose a wavelength to detect that is more suitable for your detector, for instance, visible or something like that. And the second big advantage is that wavelength tunability. Everybody that works with all these parametric down conversion sources knows that you have a lot of freedom to choose the wavelength. Even recently, there have been papers where they use terahertz radiation using parametric down conversion to image things. And so there's a lot of tunability and a lot of freedom to choose the wavelength that you want. On the other side, if you want to think of this as something practical, or you dream that this can have some practical utility apart from doing nice physics, there are certain problems. One is robustness, so that you have to make a very compact system in order to be useful outside of the lab. The second is resolution, that you have the same resolution at least that the standard commercial OCT system has. And the third is power and acquisition time. Both are related, and the more power that you have, with less time, you can have better quality images. So these things can be solved in principle. So Roche brightness, for instance, can be improved if you use a Michelson interferometer instead of a Mach-Zehnder interferometer. Resolution can be improved if you use broadband SPDC. So you go to 20, 45, 50 nanometers bandwidth, you can have better resolution, and this is not a problem. And power and acquisition times can be improved if you use first high gain PDC, that is what we are demonstrating here, and second, you use Fourier domain OCT that is faster than using time domain OCT, because in time domain OCT, remember that you have to move a mirror, and to move mechanically something always takes time, while doing Fourier domain is much better. So high gain and Fourier domain OCT can solve this problem. Okay, so let's explain more in detail what we are doing in the paper. Yeah. We are using an SU11 interferometer. So both Euler and signal are coming back for a second pass and are seeing the crystal for the second time. And we are using Fourier domain OCT. So at the end, what we are going to see here is the spectrum of S2. So the spectrum of the signal that contains information about the sample. About high parametric gain and low parametric gain, what we mean exactly. So this is a section of the paper that we have in the archive, but to be briefly, I have highlighted 3 things. Essentially, what you want is few photons per mode. So in a parametric down conversion scheme, you can have many modes at the output. It depends on your configuration, and you generate a certain number of pair photons per mode. So broadly speaking, if you generate much less than 1 pair per mode, you are in the low parametric gain regime. If you generate more than 1 pair, you are in the high parametric gain regime. And how, on what parameter depends that? So it's not difficult. You can define, or you can find a sigma, that is the nonlinear coefficient, that depends on all these factors, but essentially it depends here in the flux rate of PAM photons, that is P, that you see that is the number of PAM photons divided by the duration of the pulse, and the area of the beam. So if you focus a lot and you use a pulse source, this can be large. The parametric gain is defined as sigma L. So if this is larger than 1, you can say that you are in the high parametric gain regime. I mean, the bigger is the number, the more you are in this parameter. And experimentally, you can see, for instance, the papers of Masha, where they do this several times. To characterize this G, what you measure is the intensity, and you will obtain this dependence, is sinus hyperbolic of G, where G depends on a square root of the power, as you see here. In this fact. So you can experimentally see. In our experiments, we don't go out to very high parametric gain regime, and we obtain a G of more or less 1.7, 1.8. And this is what we obtain in terms of number of photons. So we are in the high parametric gain regime. If you will do these numbers in most of the experiments that people do, you will see a G that is very much lower than 1. And this means that they are in low parametric gain regime. So the key point to obtain this is using a PAM beam that you focus a lot, a few tens of microns, 20 microns, 30 microns, and where you use energetic pulses, and then you can use pulse. In our case, we are using picosecond pulses. Okay, there was a paper a few years ago where they demonstrated OCT in an induced coherence scheme, not with broadband, and this paper by Franco Wong and Shapiro, and they obtained these 2 curves that we will see that we can recover also with our case. You see the resolution is 2.36 millimeters. This is very large because they are not using a large bandwidth. Take into account that OCT scheme normally they have here microns. 10, 15 microns is the typical value of resolution for this case. But this is a paper that demonstrated OCT. They call it classical low coherence. I have my doubt that this is an appropriate name, but this is not the point of this talk now. Okay, so this is the scheme. Again, the sample, the laser, that is a pulse laser, the crystal. You generate signal and islet. The islet goes to the sample. The signal goes to a mirror. The PAM also goes to a mirror, come back. Everything comes back, and then we generate signal 2. So with this scheme, we can do time domain OCT. If we put here a CCD camera and we move this mirror, we are doing time domain OCT. So here we are mixing the idea of OCT with the idea of a nonlinear interferometer. And this is where we meet these two ideas that we are born in 91. No? So if you move this mirror and you put a CCD camera and you detect the signal as a function of how you move the mirror, you have time domain OCT. If instead of this, here you put an spectrometer and you look at the spectrum of the signal too, you are doing Fourier domain OCT. Yeah, so you can do time domain and you can do Fourier domain OCT with this simple scheme. You can do more, and the setup is quite versatile. So you can change when the signal one is generated, goes to the mirror and comes back, you can change its polarization. This is this quarter wave plate that you have here. And then you come back. So now effectively only the islet is seeing the second parametric time conversion process, because the signal one is orthogonal, there's no phase matching. So now at the output you have two signals, signal one and signal two, and you can measure coherence between signal one and signal two depending on what is the sample. But this is induced coherence scheme. So this is the scheme with another configuration, more a Mach Zehnder configuration that Manders demonstrated in 91. So the same scheme, only changing the polarization of the signal one, allows you to do OCT, but now based on induced coherence scheme. And you can do more. And this is something that we did in Barcelona a few years ago. Imagine now that you rotate the polarization of both signal and islet beam. This is what they are doing here. You see that the photon, you generate vertical, or here, you rotate and come back. So this is a scheme where you generate polarization in tangled photons. It's something that we did previously and no relationship with our previous work, but the scheme is the same. So you see that with the same scheme, depending, you use a single crystal, and depending how many photons are seeding the second pass by the nonlinear crystals, if no photons are seeding, you have this. If only one photon is seeding, in this case, the islet, you have an induced coherence scheme. And if both photons are seeding, you have an SU11 interferometer. So with the same scheme, just with some very minor changes, you can have a zoo of possibilities to do things. Okay, so this is a setup you can see here. So essentially what we have is a laser, is a 532 laser pulse, comes here, we have the crystal. Our crystal is a PPLN, periodic pole lithium niobate crystal, 1 millimeter crystal. Remember that we want large bandwidth, so unless you engineer the crystal, the only option that you have is to use a short crystal because you have larger bandwidth in this case. There are options to use longer crystal, but then you have to engineer somehow the properties of the crystal. It's something that we are working on that with Masha also. So you generate signal at 810 and islet at 1.5 microns. The islet beam goes to the sample, and we will change the sample a few times, and then we try to see things about the sample. And after interacting with the sample, light is reflected and comes back to the nonlinear crystal. And the signal at the PAM that are separated from the islet with a dichroic mirror go here to another mirror that you can move if necessary, comes back, and then you have parametric time conversion for the second time in the nonlinear crystals. And here you generate a signal, an islet beam, and with a dichroic mirror you can separate, and you detect only properties, for instance, if the spectrum of signal beam. So the sample is proved by islet beam at 1.5, and you detect here photons at 810 nanometers. In the case that we are doing Fourier domain OCT, we detect the spectrum. Something important that I didn't mention before about the advantages of this scheme is that here you don't have to use single photon detectors. So thinking about application and thinking about OCT here, we are not interested in particularly in entanglement or nothing like that. So here, the one big advantage when you go to the high parametric gain regime versus the low parametric gain regime is that you don't have to detect single photons. And so then this opens many more possibilities for doing OCT. here you can put, we have a mirror, and you can put an spectrometer that will work in the visible or a CCD camera, depending on what you want to measure. Remember that we can do time domain or video domain or CT. So the first examples is a very simple case. You put here a single mirror here, and here you have also a single mirror, and you move one of the mirrors. And what it will change when you move the mirror is the path length between this path length and this path length. So you are changing the path length difference between signal and island photons before coming here. So in principle, this is something that you can detect. This is the typical thing. So when we put a path length difference of 300 microns between signal and island photons, the dot curve is the spectrum, the original spectrum. Now, you put a certain path length difference between signal and island, and this we set this to 300 microns, and you see the modulation. So this is the typical information that you are going to obtain in Fourier domain OCT. You obtain certain modulation of the spectrum. You make a Fourier transform of this modulation, and the Fourier transform will give you information, as you will see, about the sample. So in this case, this is what we have, this modulation. If we now move one of the mirrors, now we set the path length difference to 220 microns. So take, this is 300 microns, this is 220 microns. So there's 80 microns different between both of them. So now what we do is a Fourier transform, and then you see here the result of doing the Fourier transform for the first case and the results of doing the Fourier transform for the second case. This is the resolution of your system, and it depends on the bandwidth. You want this to be the narrower possible, and this is the resolution. In our case, we have some 50 microns, something like that, optical resolution that is due to the bandwidth offered by our 1 millimeter nonlinear crystal. And you see, you measure the peaks, a very rude way of measuring things here. You measure from here to here, you have 80 microns. What we are doing is you change the position 40 microns, but remember that you go back. So this is twice. This is why you think here 80 microns and 40 microns. So you are detecting in a very simple scenario, a very simple proof of principle experiment, you are detecting the position of a mirror. And because you see that the spectrum change going here to here. So this is one very first case where we demonstrate that you can do OCT and to determine the position of the system with some 50-40 micron resolution. That is what is offered for by our nonlinear crystal. So now we do a second experiment where we put a sample that is a two-layer system, a two-layer sample that is 100 micron separation between the two layers, and the group index is 1.5. So the optical thickness of these samples is 100 microns. Again, we illuminate with the eyelid. We fix the signal because we are doing Fourier domain or OCT, and we determine or we measure the spectrum of the signal photons. We have to take into account central limitations that are important. So to do a Fourier domain OCT, there's an important restriction, that is the path length difference, that in this case correspond to the path length difference for the first layer and the path length difference for the second layer, should be smaller than this parameter and larger than this parameter. This parameter essentially is the bandwidth of your time conversion source. So essentially these parameters tell you are going to measure a modulation of an spectrum. So you need to have enough spectrum to see the modulation. No? I mean, you want to see the modulation of the spectrum, you need to have enough spectrum. If the modulation is too big, you are not going to see any modulation on your spectrum. So this is what is telling this inequality. The second inequality is telling you, okay, if you want to measure a modulation, you need a good spectrometer resolution. So this is fixed by that. So this tells you, okay, the smaller frequency modulation you are going to see is given by this. So then this path length difference should be smaller than that. And where this is the spectrum resolution that in our case was around 1.2 nanometers. So translated to our numbers, this means that we can be between 82 and 400 microns. But this is a problem for us. And this in the experiment was a problem for us. Why? Because you can see here what it will be the theoretical result. This is the sample. You have the first layer, the second layer. Imagine that the surface of 0 path length difference is this, and t is the distance from the first layer to this. So this is t. So if you make the calculations, the spectrum in k vector is essentially the bandwidth of your down-converted photons. You have a term that is a zero term that it doesn't carry any information about the sample, and then you have one. This is the reflectivity of the first layer, and you have a cosinus, and this is t, and then you have the reflectivity of the second layer, and this is t, and this is the distance for the second layer, because NGD will be the optical distance, and twice to go and to come back will be twice this. So you can see here that what you need is that this peak, when you make the Fourier transform of this will provide 2 peaks. If it's a cosinus, you will have 2 peaks, and 2 peaks for this and the peak in the center. So you have 5 peaks in total. But what you want is that this peak and this peak are clearly different from this 0 peak. But you can see that depending on what is t, this is not going to happen. So what you want is t as large as possible, because then this peak and this peak, when you do the Fourier transform, will be far away from this peak that carry no information, and you will be able to see the distance. Take into account that if you see this peak and this peak, the difference between the 2 peaks is 2 NGD. So when you see the 2 peaks in the spectrum and you see the distance between the 2 peaks, the distance is 2 NGD. So you are looking at the optical distance between the 2 layers. So this is useful information for you about the layer. But you need that these 2 peaks are far away and far away from the central peak. So T should be as large as possible, but in our case, we are limited by that. So the idea is that we want to make, when the coronavirus allows us to travel to Germany again, we want to do this experiment with a better spectrometer. Because if you have a better spectrometer, here you can have millimeters. And then you can make T much larger and then to go to a much more practical case. So what we did is, well, try to get information with this constraint. And then what we measure is when T is more or less in the middle of the 2 layers, this is the spectrum that you measure. You have here some modulation. You make the Fourier transform, and this is expected to be twice the optical thickness. That is 300 microns. We obtain 325 microns. This is not the ideal case. We would like to be with T very large. We didn't succeed in that because we didn't have a good spectrometer at that time. But this indeed demonstrates that we are doing OCT, because we know that for the conditions that we have, the distance between this peak and this peak is going to give us twice the optical thickness of our sample. Okay, and the last thing that we did is to see the visibility of the interference fringes that we take. Now we're going to move this mirror here. So this is in the high parametric gain regime, we expect a nonlinear dependence of the visibility. I will explain to you what is that. So now what we're going to do is the same thing. Here we put a neutral density filter where we can change the transmissivity or the reflectivity in this case. So we can go from 0 to a maximum reflectivity. And we're going to piezoelectric.
Excuse me, we have some
we
problems.
Will see a certain interference. Yeah. Now?
Yes, I think you may continue.
Okay. Yeah. So what I am saying is that now we want to determine the visibility of the interference pattern that we have when we move the path length difference between Euler and signal. For doing that, we move this mirror, and here we change the reflectivity of the sample. So we want to see how we change the visibility of the interference pattern as a function of the reflectivity of the sample. That is this one. So this is the result, and I will explain to you what is this. So the linear curve is what you find always in the low parametric gain regime. If you go to the papers of Mandels or you go to other papers where they do all these kind of things in the low parametric gain regime, they obtain a linear dependence. That is this red curve. this curve is the regime of very high parametric gain regime. This and these are theoretical curves, this and this. This is the linear regime, and this is a very high nonlinear. This is a visibility, 100%, 0, and this is the reflectivity of the sample that we put on the Euler path. Can go from 0, blocking completely the signal, to 1, no blocking at all. And here is the visibility. And this is what we obtain experimentally in our case. The green curve is the theoretical curve with the parameter that we are using, and you can see a very good match. So the important thing here is that this is non-linear. That is what you expect when you have high parametric gain regime. So you go from the linear regime, the low parametric gain regime, to a non-linear case where you have high parametric gain regime. And here you have some samples. Here, for instance, you don't have any visibility. So when you move the mirror on the sample R, you don't find any interference, in this case. Then here, for instance, you have certain visibility, nearly 40%, and you obtain certain visibility. And here you have a higher visibility. In our case, the maximum is 80% because you have losses in the signal also. So this is 80% is the maximum that we can achieve. So the green curve is the theoretical curve, and the dots are the experimental points that we obtain. So here we are showing the visibility of the interference pattern as a function of the reflectivity of the Euler, and we see the nonlinear dependence that is typical, as was anticipated theoretically many years ago for the high parametric gain regime. Okay, so essentially this is what I wanted to say. What we have demonstrated is optical coherence tomography in a SU11 interferometer in the high parametric gain regime. So we think that if you want to exploit and want to go further in the use of optical coherence tomography using these schemes, you need to go to the high parametric gain regime, because the problem with the low parametric gain regime is that you can do nice things, but you are always to have a problem with the signal, with the amount of signal that you have. And this is important because to obtain better quality images, you need larger acquisition times, and this is always to be a problem. And in this specific case, as Masha has demonstrated in many papers, you have, I would say, a lot of power available. In this experiment, we didn't use the full power that we could have used, but Masha in other papers, they have demonstrated that you can obtain very, very high signal. So, and this is what you need. Only to have a reference, in the case that you use this scheme for retina imaging, more or less what you need is 800 microwatts. Essentially, this is a reference that we normally use to see when we have enough power or not. And so if you want to use this for other applications, the high parametric regime is a must, I think. This doesn't mean that you cannot do nice things in the low parametric gain regime. And the other advantage is that you don't have to use single-photon detectors. So you can use spectrometers and CCD cameras currently available in the market. Okay, so thank you very much. And if you want to know more about that, you can contact me or one of the authors, or you can see the paper in the archive that is now under revision in a journal. Okay, so thank you very much.
Thank you for a nice talk. And so please, questions. Paulo, please.
So very nice talk, Juan. Very interesting subject. It's incredible that I used to study this induced coherence when I was a PhD student a few years ago. And it's incredible to see that now there has been, it appeared so many applications in the very interesting applications. So I have two questions. First question is, when you go to the high parametric gain, do you also have stimulated emission together with the induced coherence?
Yeah, in the second pass, yes. In the second pass, you have a stimulated emission because you have the signal and Euler coming back. You know that there's an interesting discussion, maybe you are aware of that, between Seilinger's group and Shapiro's group, about what is the real role of stimulated emission in all this process. Even I know that I think that Robert Boyd is trying to do an experiment and try to enter in this debate. So the 2 point is that when you are in the low parametric gain regime, the point of Seilinger's group, and you can see there's a paper, I think it was already published, you can find it in the archive, is that stimulated emission plays no role. This is the point of them. This is not the point of Shapiro paper, where they say that stimulated emission plays a role. So in our case, I think that it's fair to say that we are using stimulated emission because we have large power. So in the second pass, in the first part by the nonlinear crystal, no. I mean, these two papers that I mentioned, one coming from Brazil, I know Monken, they are seeding even in the first pass by the nonlinear crystal. But in our case, we are not seeding the first pass. So the first pass, it will be this vacuum. I don't say spontaneous parametric time convention because Masha doesn't like that I say that. So at least it's vacuum. You have the input is vacuum. But in the second pass by the nonlinear crystal, clearly you have signal and islet coming from for the second pass. So I would say that you have a stimulated emission. But also it would be honest to say that there's this discussion for the low parametric gain regime where they say that maybe you have, maybe you don't have. I mean, not more precise to say what is the real role of parametric, because if you make the calculations at the end, you need the islet to go through the second crystal, even if it's a vacuum, or even if it's a vacuum plus certain contribution for single photon, no? So there's the discussion. I don't know what to say about this discussion right now, but in our case, definitely I would say that we have a stimulated emission, no? In the second part for sure.
So the second question concerns what is there some kind of improvement in using OCT with this SU11 interferometer compared to other approaches? I mean, is there some improvement from the technical point of view compared to the other approaches, classical ones?
Yeah, about this, I will have to divide my answer in two parts. If you compare with standard optical coherence tomography, I would say that we have to be honest. Right now, we don't see any improvement. I mean, it's something that we are working with Masha, and I know that Sven Bramalo is working also about trying to get sensitivity limits based on fundamental principles, Kramer-Rao bounds, and these kinds of things. And it might have a better advantage in this sense. I'm not sure about that still because we are doing some calculation with Masha related to that. But I would say that I have to be honest, saying I mean, at this moment, I mean, if you want to do optical coherence tomography for real application, you have to use standard OCT. It's very good, very reliable, very good resolution, very useful. This is just an idea. It's nice physics. How far you can go in this direction to be comparable with standard OCT, I don't know. I will be skeptical in general because it's something you have to do a lot of things, and you know that to reach what standard OCT can offer. Now, the second part of the answer is, well, but it's better SU11 that induced coherence scheme. If you asked me this question a couple of weeks ago, I would say, well, SU11, it seems more robust. It's a Michelson interferometer, essentially. It seems more robust than a Mach-Zehnder interferometer, as is the other one. No? But in the last few days, something that I have to talk to Masha also, we have found that maybe induced coherence scheme, you have more freedom. Remember that we were talking about the importance of the T. Where is the point of zero path length difference? That in SU11, this is very important, this is very large. But maybe in the case of induced coherence, not so much important. And then there will be an advantage for an induced coherence scheme because you can go to T equals 0, for instance, you can put the point of zero unbalancing of zero path length difference in one layer and everything will work fine. So I am not completely sure now that SU11 is better when compared with induced coherence scheme. So I mean, seeding only the islet beam or seeding signal islet beam is better. I don't know. I would say that it's not clear and we have to make more calculations about that. Yeah.
Very nice. Thank you very much.
Thank you, Paulo.
Maria, please.
Yeah, I wanted just to add something to what Juan said. One thing is obvious, that of course practical, in terms of practical parameters that are achieved by this induced coherence or SU11 compared to standard OCT, of course they are incomparable, because classical OCT reached a fantastic level. But there is still the advantage that one can use a different wavelengths to detect. Right, so that the probing wavelength is different from the wavelength that we detect, and this is for all modifications of this OCT with undetected photons. And the second point I wanted to make is that actually what Juan said about the consideration about the non-sensitivity to the position of the sample is something new for me. I didn't know. It's something Juan discovered recently, and I wasn't aware. But what I know is that SU11 interferometer is good at beating short noise limit, for instance, in phase, in detecting phase displacement. And also in absorption measurement. This we know that if we put some kind of phase delay or absorption, then the measurement is better than classical measurement allows. And I do believe that here we also have these resources, but we haven't studied them yet.
Mm-hmm.
Thank you. May I just add to this question my point? So we have also quantum optical coherence tomography based on Hongo-Mandel interference. And in this case, we have an advantage that we have dispersion cancellation. Have you got this advantage in your case?
I don't expect to have dispersion cancellation, something that we have not measured, but I don't expect. The advantage, I mean, I see between this Hongo-Mandel, what used to be called quantum OCT, no? But this Hongo-Mandel is that they are using G2 measurement. This is correlations, and we are using G1 measurements. It's always simple. So they need to use coincidence. So then the problem that I see is that you cannot go to the high parametric gain regime, because then these correlations that are embedded in principle, I mean, these correlations that are embedded in the G2 probably will disappear. But it's something that I am just talking without having made the calculation. But what is clear is that this quantum OCT was proposed by the group of Boston. You need to do G2 measurements, so you need to measure coincidence. While in this case, that use SU11 induced coherence, you don't need to make it's a G1 measurement, so you need only signal, and you measure the spectrum.
Yes, thank you. It's clear. Xiaoson, please. Xiaoson Ma, could you ask? We don't see, don't hear you.
No.
Yeah.
Oh, okay. Somebody's trying to ask, but
disconnected.
Hello?
Yeah. Yes. Okay, we have some problems. Okay, maybe later. Okay, Ranjit, your question, please.
Yeah, thank you. Thank you for your talk. I have two questions.
Now? Can you hear me now?
Okay. Juan,
Hello?
please continue.
Yeah.
Excuse me, Ranjit, you may continue.
Okay.
Next question for
Okay.
you.
Okay. So first question is, when you talked about low and high parametric gain regime, do you mean that PPLN crystal allowed you to use higher values of nonlinear effective coefficients? This is the first question.
What I mean, no, the nonlinear coefficient is the same in the low and the low and high parametric gain regime. What it happens is that the number of down-converted photons that you generate is much higher. So the point that you have low or high parametric gain regime is not that the nonlinear coefficient change. You see here. Let me show you. Yes, let me show you one moment. Yes, here you see the nonlinear coefficient, that is chi2 square, this value, this doesn't depend of the region you are. What it changed is essentially the number of pumped photons that you have per second and area. So if this is large enough, you can have many pair photons generated per mode. And this is what makes the high parametric gain regime. So if you have a value of G, so the number, essentially G is the number of photons that you generate, very low, then you are in the low parametric gain regime. Normally, if you use continuous wave pumping, you are in this low parametric gain regime. I remember there's a paper, a very nice paper by Professor Silberberg that unfortunately passed away 1 or 2 years ago, where they use, I think that is KTP crystal, and they told me 1 or 2 watts of pump power, continuous wave pump power, 1 or 2 watts. They generate a lot of photons in a 30 nanometers bandwidth, and they are still in the low parametric gain regime because they generate very few photons per mode. In our case, we generate more. Right? You see the number here that we calculated. You can generate, let me see, one moment. You can generate 7 pair photons per mode, and this is high parametric gain regime. When you have more than 1, you are in the high parametric gain regime. When you generate very less than 1, 0.0 something, then you are in the low parametric gain regime.
Mm-hmm. Thank you. Second question, what type of nonlinear processes you are quasi-phase matching by using PPLN?
Yes. Yes, I mean, it's a crystal where I don't remember now what is the period of the crystal, but this is a standard crystal where you use a constant period and then to obtain the phase matching. One thing that we plan to do in the near future, as soon as we can continue, is to use other kind of crystals where you can engineer the phase matching by changing the period, for instance, in order to have a much larger bandwidth. No? Remember that you want 30, 40, 50 nanometers in order to have a very large bandwidth, because then resolution improves a lot. But in this case, in our experiment, this is a standard PPL lithium niobate crystal with, I think it's 10 microns or something like that, no? 7 microns period, so it's quite a standard crystal.
Mm-hmm. Mm-hmm. Okay, so if you are quasi-phase matching 2 nonlinear processes, this is for my comment, yeah. Then in that case, since you are studying polarization properties, then in PPLN, if you're using 2 nonlinear processes and then you are quasi-phase matching them, then
yeah.
We don't hear you.
Lost.
Okay.
Yeah.
I'm sorry for this. Xiaosong, your question now, please. We still don't hear you.
How about now? Can you hear me now?
Yes.
Yes.
Hello?
Yes.
Yeah.
Okay, great. Thank you, Juan, for your very nice talk. So going back to the last slide you showed your data. I kind of mixed the points. That's why a high gain parametric process will enable the less sensitive to the loss. For example, if you look at the red,
Can you repeat, please? I don't hear very well.
Okay. So my question is, can you give us intuitive understanding why high gain parametric conversion provides more susceptible to the loss? Okay, because it basically saturates at the starting from 0.5 reflectivity.
Yeah, because this is just the point where you have the same reflectivity in signal annihilator. What we guess is that when you have the same reflectivity. It's something that was a surprise for us. I have to recognize that when we were making the calculations, so we have this experimental curve, and we didn't understand. In fact, we had some problems to try to figure out why this was the curve. No? But when the calculation, we were surprised to see that when you want the very high parametric gain regime, you can have 100% visibility, even though you have losses. And we were surprised to see that. So, I mean, the explanation I can give you, I mean, the point is that this only happens when the reflectivity is the same in signal and Euler path. So in this case, I mean, I don't know if it's an intuitive explanation, but this is the only explanation that I have, is that the system doesn't care when you have the same reflectivity. So it's the same thing. So when you don't have, when the reflectivity, I mean, if one of the R is the reflectivity is 1, you have only high visibility, 100%, if the reflectivity is 1 also in the other case. But here, when you have the same reflectivity or the same losses in the signal and Euler path, then you can have 100% visibility. It's something that we would like to measure to verify that really you have the 100% visibility, even though you have losses. Something that I think will be in general unexpected, no? At least as expected that it was to us, no? Because the general rule is that you need high reflectivity 1 in order to have 100% visibility, no? I don't know how intuitive is that, but it's the only explanation I have, and that it's the point that you have the same reflectivity in both R's that makes the 100% visibility. But we plan to make an experiment, try to see that really this is the case.
Yeah, it's kind of strange, because if you look at Mendel's original paper, they talk about, I mean, like every other interference paper, they talk about indistinguishability. And one thing I can think about is when you have loss, it introduces indistinguishability in amplitude or in the photon number.
Yeah, you are right, but sorry. Yeah, you are right, but one has to be careful. Yeah, no, one has to be careful when we, I mean, the original explanation of this induced coherent effect by Mandel's group was this, what you say, this indistinguishability, no, between the path taken by the photon. But when you go to the high parametric gain regime, it's more difficult to talk about indistinguishability, because now you have photons in both paths always. It's not that in the low parametric gain regime, you can say, well, the pair of photons is generated in one crystal or is generated in the second crystal. So you can say, okay, how I know in what crystal the photons are generated, and then you can talk about distinguishability. But when you go to the high parametric gain regime, you are generating photons in both crystals at the same time, because you are in this regime. So we have to be careful about how to, I don't say that distinguishability or indistinguishability out of the question, but one has to be more careful about how to talk about distinguishability in this case of high parametric gain regime.
Is it possible that in the high gain regime, that's the generated photon number is so large, that's probably the loss introduced is not as significant as the single photon regime, like the red dashed curve you plotted?
Yeah, maybe. I mean, the question with the low parametric gain regime is that you have clear measure of distinguishability. No, you can use some measures where clearly tell you how distinguishable are the options, and then you can relate to that. No, and this is important. But as I told you, it's not that distinguishability cannot be used, but just I think that has to be used in a different way. Because in the case of low parametric gain regime, it's very clear what you mean by distinguishability, but in the high parametric gain regime, it's not so clear to me how to interpret the concept of distinguishability.
Okay, thank you.
Thank you.
Okay.
Masha, I think he wants to say something.
Yeah, I want to add that, first of all, I didn't think much of it either. I mean, I didn't have good explanation either, but now I came to thinking actually this is not interference. It can be considered as parametric amplification, right? And de-amplification. So what happens depending on this phase is that the incident light is amplified or de-amplified, and this amplification is huge, and so it shouldn't be treated like the ordinary visibility. Maybe this is the answer. I'm not. I don't think I can give a good answer to this really good question, but I think that the difference is that usually for interference, the visibility is the maximum of signal is given by just the incident intensity, yeah, and here it can be much higher because there is amplification in the second crystal.
Okay, you mean this is phase sensitive amplification?
Yeah, this is phase sensitive amplification, of course. SU11 gives you phase sensitive amplification. Yeah.
Okay. Yeah.
Can I make a part, Xiaosong? Just
sure.
Because it's a very interesting topic. What I'd like to comment on the part question is that it's not surprising for me that you can achieve a high visibility with losses, because you can have the coherence can be induced by the presence of both signal and idler fields when in the second pass of the pump. Then it's not surprising for me, but it's very surprising that without losses in the same conditions, the visibility decreases. This is what I think is surprising.
No, but you have so in this case, the curve, you still have the signal losses. So in this plot that I'm showing you, this plot that you have in the one axis you have Euler reflectivity 1, but in the signal you have losses. So in all this plot you have losses in the signal. That is 0.6 or something like that. So
the losses are not equilibrated when you reach 1. Yeah. Okay.
You have 0.6, I think, losses in the signal, but this is always everywhere. Just when the losses on the signal and Euler are equal, you have 100%. But you have always. So in this point that you expect 100% visibility because the Euler has 100% reflectivity, you still have the losses of the signal.
Then it agrees with my attempt of explanation, because if losses are equal, then you just seed by 2 beams. You seed the second crystal by 2 beams, signal and idler, and there will be phase sensitive amplification. If the losses are not equal, then you have unbalanced seeding, and it means that you have partly phase insensitive amplification. This is my intuitive explanation of what happens. Yeah, and I think it agrees with what has been said. Yeah.
Okay. Okay, maybe I have one more question. If you want to achieve a better resolution, you need to have a more broadband source.
Yes.
Yes. But if you are working in Fourier domain, maybe it is possible to tune the crystal during the scanning of spectrum in order to tune the degeneracy of the regime, and so you collect several spectrals and reconstruct full the spectral range.
Yeah, you mean to take many different wavelengths with short bandwidth? Yeah. Yeah. This has a name. This is swept source OCT. So they do it. I mean, instead of having a very large bandwidth, so you have you move the wavelength of your source. Large, and then you take measuring for it. This is a very good idea. It's something that is called, I think, swept source OCT or something like that. And some applications in standard OCT use this technique in order to avoid to use a source with very large bandwidth. You have effectively a large bandwidth, but just by running, by changing the wavelength of your laser. Yeah, thank you.
So the same thing can be done with this SU11 interferometer.
Yes, I would say that most of the things that you can do, I would say nearly everything that you can do with standard OCT can be done with this SU11 with induced coherence scheme. Yes.
Okay. Okay, if there are no more questions, okay, we may finish. So thank you again for a very interesting talk, and I also invite all of you next week to our next seminar, and see you all next week.
Thank you very much for the invitation. Thank you very much to everybody. Bye bye.
Very nice to see you all.
Thank you.
See you next week.
Bye
Bye bye.
Bye bye.
bye. Para salir de aquí.